Hello everyone, welcome to Computer Science Hub. Our subject is Computer Fundamentals, topic Error Detection and Correction Codes, Parity Bit. Okay, so let's start with error detecting and correcting code. Digital circuits are normally designed with extreme accuracy, such that the probability of occurring even a single error is very small. Okay, digital circuits are designed like that. Um, they're designed with extreme accuracy, so there will be less chances for occurring a single error. Even then, of course, we have designed the digital circuit with extreme accuracy, but even then, errors may occur as digital codes are being transferred from one point to another within a digital system, or while codes are being transmitted from one system to another. Okay, the errors can occur in digital codes in the times when they are transferring from one point to another in a system, or they are transferring when we are sending a data from one system to another system. The bits may change, errors may happen. The errors take the form of undesired changes in the bits that make up the coded information. So, the term errors means in the digital coded data, the errors are the undesired changes in the bits that make up the coded information. That is, a 1 can change to a 0 or a 0 to 1 due to component malfunctions or electronic noise. That means, suppose we are going to send a data like 1001, and at the receiver side, he receives the data as 1010, which means the data is changed. There comes an error, right? A 0 is changed to a 1. So that's the type of errors that may happen in digital circuits. The errors may take the form of undesired changes. The some methods of detection and correction of errors in information cores is commonly used in digital system. So we need accuracy, right? If we are communicating through digital codes or digital system, we need accurate data. So and we have already told that there are some chances for malfunction, component malfunctions or electronic noise by which our digital data may change, and undesired changes in the bits may happen. So some methods are needed to detect those errors, those changes, and if possible, correct those errors to get the original data. There are two strategies for dealing with errors. First one is to include enough check bits along with each block of data sent to enable the receiver to deduce that an error occurred, but not which error. These types of codes, which can only detect errors, are known as error detecting codes. Okay, two strategies for dealing with errors. The first one is the error detecting codes. In error detecting codes, we include enough check bits. Suppose we are sending a data in 4-bit blocks. Okay, we have 3 blocks. Okay, so first block contain 4 bits, second block contain 4 bits, third block contain 4 bits, and that 4 bit is our original data, and we are adding enough check bits with this data. Suppose we are adding 2 bits each. Okay, so with the first 4 bit we are adding 2 extra bit, second 4 bit we are adding 2 extra bit, and for third 4 bit we are adding 2 extra bit, which means we are adding redundant data, or we are adding extra data, extra bits along with the original bits, and these extra bits are included to deduce that an error occur. These extra bits are included to detect errors. Okay, and these bits indicate that error has happened, but we cannot identify where that error happened, where that error occurred. We can just say that this data is not the original data, which means these codes can detect errors and they cannot correct errors. Okay, these types of strategy is known as error detecting codes. For error detecting codes, and there is a criteria for error detecting code. The minimum Hamming distance between any two codes must be at least 2. Then, if a single error occurs in one of the codes, this can be detected because the corrupted code will be different from the codes allowed in the group. To make it happen, in case of error detecting codes, we need that the minimum Hamming distance between two codes must be at least 2. We know what is a Hamming distance. Okay, we have already discussed in our previous classes. Hamming distance, and this Hamming distance must be at least 2. Okay, we need a minimum of Hamming distance 2 in case of error detecting code. So, if a single bit changes, single error occurs, our pattern will be different from this Hamming distance. Okay, so this is our there's a fixed pattern. This is our pattern. Our Hamming distance between must be at least 2, and if a single error occurs in one of these codes, that error can be detected because that character code will be different from the codes that are allowed in the group. In our group, our Hamming distance must be at least 2, but if a single bit changes, then this strategy will change. So this is the case of error detecting codes. The other way, the second strategy is to include enough check bits with each block of data sent to enable the receiver to deduce what the transmitted data must have been. This type of codes that can both detect and correct errors are known as error correcting code. These are the two important points. In first strategy, it deduces that an error occurred but not which error. In second strategy, it can deduce what the transmitted data must have been. Okay, these are the two different categories. So in the first category, we already discussed that we can identify that an error occurred, but we cannot deduce which bit occurred, in which bit that errors occurred, or what is the original data. We cannot assume that, and such kind of data are known as error detecting codes. And in that, to make that happen, our Hamming distance must be at least 2. And here in this error correcting code also, we include enough check bits with each block of data, and but here the receiver can deduce what transmitted data must have been. That means the receiver can find that an error has happened and errors occurred, and in which bit the error occurred, and he can easily deduce the original data. Okay, and this is known as, these types of codes were the which can detect and correct errors are known as error correcting codes, which can detect only are known as error detecting codes. Then the concept of parity bit. A parity bit is a bit that is added to ensure that the number of bits with value of 1 in a given set of bits is always even or odd. That means a parity bit makes count of the number of ones. Okay, our digital data will be a combination of zeros and ones, right? And our parity bit makes count of number of ones, and it will always set like either the number of ones will be always odd, or the number of ones will be always even, based on which type of parity is that. In even parity, the number of ones will be always, the total number of ones will be always even. In odd parity, the total number of ones will be always odd, like that. Okay, so this is the definition. A parity bit is a bit that is added to ensure that the number of bits with value of 1 in a given set of bits is always even or odd. Parity bits are used as the simplest error detecting codes. Okay, we have discussed two strategies, error detecting and error correcting. So we are discussing with the first strategy, so that is error detecting code, and error detecting codes, parity bits, they are used as the simplest error detecting codes. Okay, this is a parity bit is a tool for error detecting codes. Two variants of parity bits are, first one even parity, and second one odd parity. Okay, an even parity bit. Okay, listen this point. This point is very much important. An even parity bit is set to 1 if the number of ones in a given set of bits is odd. Okay, we have given a digital code containing a sequence of zeros and ones. Okay, in that code, if the number of ones are equal to an odd number, the number of ones are odd, then the parity is set to 1 in case of even parity, which means the total number of ones will be even. Consider an example. Okay, suppose this is our data bit. Okay, this is our data bit. Here, total 4 bits, and in that 4 bit, 3 bits are ones. The number of ones is 3, which means the number of 1 is odd. If the number of 1 is odd, in case of even parity, it will be set, the parity bit will be set as 1, which means I have added a 1 over here. So the total number of ones, including the data bit and the parity bit, is what? 4 even number. So the concept is, for even parity, the total number of ones including the parity should be an even number. In odd parity, the total number of ones including the parity bit should be an odd number. Okay. An odd parity is set to 1 if the number of ones in a given set of bits is even. Okay, this here for an even parity it is set to 1 when the number of bit is odd. For an odd parity it is set to 1 when the number of ones is even. Okay, and I think the second method is easier to remember, right? For an even parity, we are making the total number of ones equal to an even number. For an odd parity, we are making the total number of ones including the parity. Total number of ones mean the number of ones in the data bit plus the number of ones in our parity. So the total number of ones should be an odd number. This is the concept. Okay. If the parity bit is present but not used, it may be referred to as mark parity, where the parity bit is always 1. These are the two important concepts or two important terms we should know. What is a mark parity? It's like one word questions. What is a mark parity? Here, a parity bit is used but is not. A parity bit is present but it is not used. And here the parity bit is always 1. Either the number of ones is 1 or 0 or something like that. We don't bother about it. The parity bit is always 1. Such type of parity is known as mark parity. Or if the parity bit is always 0, regardless of the number of ones and zeros, then our parity is known as space parity. Okay, so study these two terms. Mark parity is the parity bit is present but it is not used and it is always equals 1. The space parity is the parity bit which is always equals 0. Parity bit checking is used occasionally for transmission of ASCII. We know our ASCII is a 7-bit ASCII. We know that ASCII characters are ASCII 7 is 7-bit characters. So this ASCII having 7-bit and we can easily add an 8-bit character as a parity bit. So the 8-bit can conveniently used as parity bit. The 7 bits are data bits and the 8th bit is a parity bit. A parity bit checking is occasionally used in ASCII characters. Consider this example. Okay. Here the 7-bit of data number. Okay. This is a 7-bit of data and we are adding one parity bit and making it 1 bit. Okay. And here the parity bits are added at the end. Okay. Usually we will be adding it at the first place. Okay. And here the parity bits are added then and those I have shown in bold as our parity bit. So here 7 zeros are here. 7 zeros means the number of we are concentrating on the number of ones. Here the number of 1 is 0. The number showed in bracket are the number of ones. Okay. So number of 1 is 0. What we have to do is to make all number of ones into an even number, right? In case of even parity, we have to make it an even number. That means this is our parity bit. This bit, we have to add this bit. If we add this as 1, what will happen? The total number of ones will be odd, right? So, we selected 0 for our even parity. This is our even parity bit added number. Consider for odd parity. For odd parity, we have to make the total number of ones as an odd number, right? So I have added here a 1. A 1 is added here. Consider the next example 1010001. The number of 1 is 1, 2, 3. Okay, the number of 1 is 3. For even parity, we have to make the total number of ones including the parity bit as even. So we will add a 1 in place of parity bit, right? The total number of 1 become 1, 2, 3, 4, an even number. In case of odd parity, what we have to do? We have to add a 0, right? Because if we add a 1, our total number of ones will be 4. But for odd parity, we need the total number of ones should be an odd number. So here I have added a 0 over here. Then our total number of ones is equal to 3, which is an odd number. Next, here 4 bits are there, right? 4 ones. Then the total number of ones is 4. It's already an even number. So for even parity, we can add a 0 to make it even, right? For odd parity, we have to make it an odd number. So I have added a 1 over here, which means the total number of ones is 1, 2, 3, 4, 5, an odd number. Consider this, here 7 ones, which means odd number of ones. We have to make it even for even parity, and I have added an extra one for the parity bit. And for odd parity, the number is already odd, so I have added a 0. This is the concept. Okay, this is the concept of parity. Then a parity bit can be computed as follows. Okay, this is the concept of error detecting codes, how we can compute a parity bit and how we can identify that an error has occurred. Let's check this. Assuming we are sending a simple 4-bit value, we are sending the value 1001 with the parity following on the right. Okay, parity bit is added on the right, and this is the XOR denoting XOR gate. This is not XOR gate. Okay, the transmission send using even parity. We are considering the even parity scheme. Suppose A wants to transmit 1001, right? Then A computes the parity bit, and we have said that how to select an even parity or odd parity is like we have to count the number of ones and check whether it is even or not even or odd, and we have to make the total number of ones including the parity into an even bit, even number. But actually what computer is doing is like it finds the XOR of individual bits. Okay, it finds the XOR operation between the individual bits. 1 XOR 0 XOR 0 XOR 1, and the result will be our parity bit. And the concept is same. What we have done manually is done using this XOR operation. Okay. 1 XOR 0. We know for XOR operation, if the bits are same, the result will be 0. If the bits are different, the result will be a 1. So here two zeros, right, and two ones. Of course, our result will be a 0. When we are finding the individual XOR, first perform 1 XOR 0, which means the terms are different. Our result will be a 1. And that 1 XOR again X 0. Again, terms are different. Our result will be a 1. And that 1 across this one, XOR this one, means the bits are same. So our result is a 0. So our bit is 0. And then we have A, find out the parity, right? A parity bit is 0. The next step is to add that parity and send the data. A want to transmit 1001. A computes the parity bit and the parity bit is 0. Then A adds the parity bit and send it. So our data is 1001 and our parity is 0, and this is our data. A wants to transmit this data now. Then A transmit this data, and no error occurred in between, and B receives the same data 10010. Okay, and both A and B know that this our scheme is even parity scheme, right? Then B receives 10010. Then B computes the parity by XORing each individual bits. 1 XOR 0 XOR 0 XOR 1 across 0. Then 1 XOR 0 is 1, 1 0 is 1, then 1 XOR 1 is 0, then 0 XOR 0 is 0. So we got a 0 over here, right? B reports correct transmission after observing expected even result, which means in our B knows that in our result only two ones are here, right? For two ones, we have to add 0 as our parity bit to make it an even number, and B got 0 as its parity bit. So B reports the correct transmission after observing the expected even result. Okay, consider the next case. Transmission send using even parity. A wants to transmit 1001. First, A computes the parity bit 1 XOR 0 XOR 0 XOR 1 and the parity 0. A adds that parity and sends 10010. But during the transmission time, some error has occurred and B receives 11010, which is not same as A was sent. A sent 10010 and B receives 11010. Okay. Some error happened, then what B perform is to compute the overall parity. B compute the parity 1 XOR 1 XOR 0 XOR 1 XOR 0, and we will get 1 XOR 1 is 0, that 0 XOR 0 is 0, that 0 XOR 1 is 1, and that 1 XOR 0 is again a 1. Okay, so that is a 1, and okay, so B got a result as 1, right? B got the parity as 1, but in our data, the last bit, the parity bit is 0. There is a mismatch, right? B reports an error after observing unexpected result. B expects 0 because our parity in our A adds the parity bit as 0, and B receives this data and the parity bit, and B checks whether this parity is correct. For that, B performs the individual XOR operation, and the result of this XOR operation is 1, but our parity is 0. There is a mismatch. B reports an error, and B found that there is an error, but B cannot deduce on which bit that error is occurred. So B cannot deduce what B just deduce that B just say that an error has occurred, but where that error has occurred, what is the actual data, B cannot say anything regarding that. So this kind of transmission is, or this kind of parity system is error detecting code, and this is the use of parity bit. Okay, okay, okay. This is all about our error correction and error detecting bit introduction, and we have discussed what is an error detecting transmission error detecting code and about parity bit. Hope the concept is clear. In next video we will be discussing about hamming codes. Okay, okay then, thank you.